Okay, module 15, OYOs. Let's start with number 1. See if I can get it good. What is the value of the equilibrium constant for the following reaction? Here's our reaction right there. Now, we know that our equilibrium constant, it is built out of this, that equation, that reaction. That's our constant. K equals the concentration of C to the stoichiometric coefficient of C, concentration of D to the stoichiometric coefficient of D, all divided by the concentration of A to the stoichiometric coefficient of A, concentration of B to the stoichiometric coefficient of B. So I'm not going to say that each time, but that's what we're working with. I'll show you and we'll have another name for it, but that's what we're trying to work with. All right, so if we go ahead and fill that out, our C's and D's are on our product side, our A's and B's are on our reactant side. Here is our K placed according to what the reaction looks like. And then we have our information. The equilibrium concentration of N2 is 0.242 molarity. The equilibrium concentration of H2 is 0.468. And the equilibrium concentration of NH2 is 2.28 molarity. So I'm going to plug those in right where they go. And I kind of put arrows as to where all the numbers went. So here's where they are put in all together in the proper order. I went ahead and multiplied it out because I was trying to show my steps. So I end up, this is what it's going to be the final step. And when I multiply it completely out, I get 212.18, 1 over molarity squared. And they said 2.10 times 10 to the 2, 1 over molarity squared. Okay, number 2. A chemist is studying the following reaction. There's the reaction. The chemist starts with, and we have all of our numbers, starts with 2.6 molarity of SO3 and no SO2 or O2. He finds that the reaction reaches equilibrium when the concentration of SO3 reaches 0.40. At that point, the concentration of SO2, which is here, that's his product, is 2.2 molarity, and the concentration of O2 is 1.1. What is the equilibrium constant for this reaction? Now remember, we have our, up here, our C to the C times D to the D divided by A to the A times B to the B. So we're going to go ahead and build that. And we build that with our letters first, so we kind of keep track of what we're doing. So we have our products on the top, double checking that they're all gas, because remember, that's what we have to do our math with is gas. If it's something else, we can't use it. Aqueous or gas, we have concentrations, but the other two no. So our products go on top, our reactants go on the bottom. When we fill that out according to the numbers, so we're just plugging in these numbers where they're supposed to go, it looks like this. As we multiply it out, we get to here, and that's just the secondary step that I do just to show you what it looks like. When we do the math, we get K equals 33.25 M, and they said 33. All right, number 3, 15.3. In example 15.1, the equilibrium constants of 2 equilibrium reactions were calculated. For each reaction shown in the following table, tell whether the equilibrium is weighted toward the reactants, weighted toward the products, or balanced between the reactants and the products. So we're looking at our reaction. There's our reaction here. This is what it looks like. And this is our K. So remember, K is is what we're trying to use to measure to see whether it's our equilibrium is weighted toward the products or towards the reactants or neither. And the first one, it is weighted. It's 463, which is quite high. So the products are bigger because the products end up on top, and so it makes this answer large. So it's weighted toward the products. In this problem, the number is quite small. That's a -6, so we know it's teeny, very, very small. So the reactants, remember the reactants are on the bottom of that equilibrium equation. And since it's so small, then the reactants are very, very large, and it's weighted toward the reactants. All right, 15.4. 15.4. 3 chemical equilibria, which is the plural of equilibrium, are written below. Next to each equation, the value of the equilibrium constant is given. If any of these equations can be written with a single arrow, do so. Make sure that the arrow is pointing in the proper direction. This one, so we look at this, here's our K for A, and the K is 4.6 times 10 to the 4th, so that's, 46,000 or whatever. It's very large. So it's weighted toward the products. So the arrow should go like this, should be this way, right? Goes that way. On B, the K is 3.2 times 10 to the minus 14th. So it's very, very small. So it's actually weighted toward the reactants. So it goes like this. Now the problem is when it goes backwards, that's not how they write it. So we should make it 4HCl plus O2, and then the arrow in the right direction, 2Cl2 plus 2H2O. And then if you look at that, we actually have an acid equation. We have our acid, and then it breaks down to salt and water. So that's what we're looking at. And in C, the K is 1.2, so it's very close to 1, so we can't change it at all. All right, 15.5. Give the expression for the equilibrium constant of this reaction. So here is our reaction here. Remember, our equilibrium constant can only work with aqueous and gas. It cannot work with liquid or with solid because you can't affect the concentration of either of those. Those are going to be what they are. You can add weight or add mass, but you cannot add concentration. They just are what they are. So we know this is our formula, K equals C to the C times D to the D, all divided by A to the A times B to the B. And because it doesn't, the C and D's are our products, our A's and B's are our reactants, those go away. So we just fill those in and we get K equals LiOH, and we square that because our exponents are our stoichiometric coefficients. So we square that. H2 does not have any stoichiometric coefficients, so it's just H2 with its brackets, and the brackets mean we're talking about concentration. Okay, 15.6. What is the equation for the equilibrium constant of the following reaction? And we look at this throughout, and the first thing we need to do is to make sure we're dealing with only what is important. So we're crossing out our solids. There's 1 solid, 2 solid, both in the reactants. And then we have a liquid, H2O, in the product. So none of those count, which is hallelujah. Our equilibrium constant is this that we've talked about before. Because the reactants are null, we're not going to deal with those at all. So we can cross that out. So now we're just going to plug in what we have left. K equals NH4OH, and because the stoichiometric coefficient is 2, we put it as an exponent there, so it becomes squared, and then BaSCN2, and again, those are concentrations. All right, for 15.7, a chemist is studying the following reaction. The reaction has an equilibrium constant of 17 m cubed. The chemist measures the concentrations of each substance, and he goes ahead and lists them out for us. So there's our list. Is the reaction at equilibrium? If not, which way will it shift to attain equilibrium? So we know that 17 is our K, so we know that's what we're trying to aim for. And we have our current concentrations of each of the items. They're all 3 gas, so we have to use them. So we're going to go ahead and plug them in. We're using that same formula we've used before. We have K equals N2 times H2 cubed, because look, there's our stoichiometric coefficient. We have to cube it because it's a 3, all divided by NH3 squared because our coefficient is 2. So when we plug all those numbers in, and I went through a secondary step just to keep track of what I was doing, we get 47.53 m squared, which is a whole lot more than 17 m squared. So since this is higher, then we have to, than the original, right? It has to shift towards the reactants. We have to get those reactants to be higher. We have to get this number higher to lower this total number closer to 17. So the shift has to go toward the reactants. Okay, 15.8. Assume the following reaction has achieved equilibrium. What will happen to the concentration of CO and CO2 if extra H2O is added to the system? Now, we better check to see if this is all workable. It's gas, 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 and gas. Okay, so everything's going to work. If we add more H2O over here, if we add more of that, they're asking what's going to happen to CO and CO2. Well, we know that the concentration of CO, if you add more H2O, the CO will be used up because it's gonna flow this way. It'll flow back this way. So this will get used up and more of this will be made. Because remember, in equilibrium, we've got stuff flowing this way being made and then stuff flowing this way being made. So if you add H2O, your CO will go down because it's going to be used up and we're going to make some more CO2. All right? And I wrote that down here. Okay, with 15.8, I rewrote this so that we keep track of it. So the question is, and this is a continuation from the previous question, what will happen to the concentration of CO and H2O if CO is removed from the system? So if CO is removed, then what's going to happen to H2O and CO2? Well, if this is removed, then this can't do anything until suddenly this springs into action and it reacts with H2 and starts to make CO. So CO2 will go down because it's being used up in order to make CO. And so then because this CO is being made, the other product is H2O, so H2O will go up as well. So CO will go down because it has to be used to fill the gap for CO. And then the H2O will go up because if CO is being made, so is H2O. All right, and C, what will happen to the concentrations of H2O and H2 if extra CO2 is added to the system? So if we get more CO2, if there's more CO2, the question is what's going to happen to H2O, right, and H2. So if even more CO2 is added, then the H2 is going to go down because CO2 and H2 are going to combine to make our products. So H2 will go down, but H2O will go up because more of the products will be made because we have all this extra CO2 that has to be dealt with. So it'll have extra being made. All right, and that's what I wrote down in my answer. Okay, 15.9. Assume that the following reaction has already attained equilibrium. So there is what it looks like. And the question A is, which way will the reaction shift if pressure is decreased? And we know if pressure is decreased, according to our rules, it flows the way toward the most gas molecules. These guys have 3, this one has 2, so if the pressure is decreased, it will go toward the reactant side because the reactants have more gas molecules. And then what will happen if the pressure is increased, then it will go toward the products because it goes toward the side with the least amount of gas molecules. Okay, number 15.10. Consider the following reaction that has already attained equilibrium. We have a delta H here that's a negative 132. So we've got to plug this into our system so we can do our problem. And because it is a negative, we know that this is exothermic. and it goes on the product's side. So we go ahead and put it on the product side, and we want to physically do that so we can keep track of what's happening. Question A, what will happen to the amount of CaCO3 if the temperature is raised? Well, we know that the flow goes away from that. If the temperature is raised, it goes away from where the energy is. So if the temperature is raised, the flow shifts away from the energy, and the CaCO3 will decrease because it's on the side with the energy, and the flow changes when the temperature is raised to go away from that. And then what will happen to the concentration of CO2 if the temperature is lowered? So if the temperature is lowered, it goes toward the energy. So the momentum or the movement of the reaction goes towards where the energy is. And since that's the case, the CO2 will in fact decrease. All right. Okay, 15.11. What is the equation for the acid ionization constant of HClO2? Now remember, with our the acid ionization, we're trying to take apart this acid and separate it into its H positive components, and then whatever component would have accepted the H positive. So we just separate it out. There's our H positive plus ClO2 negative, because it becomes charged once that H is pulled away from it. And our K sub A, we put our products on top, and we divide by our reactants. And so we just plug those in. H positive, the concentration of that, times the concentration of ClO2 negative, is divided by HClO2. And there's no stoichiometric coefficients, so we don't have to worry about those. Okay, 15.12. What is the equation for the base ionization constant of pH3? So with pH3, when we looked at it, according to our book, when we're having a base ionization constant, we have to look at what happens to the pH3 or the base when we add water, and then we see where the H can go away, and we end up with an O2 negative. So our equation looks like this: pH3 plus H2O. H2O is a liquid, so it's not going to count for anything. Makes pH4 positive, right? Because the H from H2O has to be absorbed in the pH, because that's what a base does. It takes the extra H. In this case, the water is in fact the acid, and then we are left with OH negative. Again, when we're making our base ionization constant, K sub B, we just take what we have in the products and we divide it by what we have in the reactants. In this case, H2O being water, being a liquid, it doesn't count in our calculations. So we just put the two products on top and divide it by the reactant. Because there's no stoichiometric coefficients, we don't have to worry about those as exponents, and we just plug it in just like that. Now they wrote it OH negative first and our pH4 positive second. I don't know if that matters, but that's how they did it. All right, and 15.13, equal concentration aqueous solutions are made with the following four chemicals. The pH of each solution is written next to the chemical formula. Identify the acids and the bases and in addition indicate their relative strengths. All right, so remember in your book we had that colorful little diagram, and so it goes from 0. In fact, in your book it goes even negatives over here. But basically we go from 0 to 14. 7 is our pH 7 is a neutral. And then when we go further down, any pH less than 7 is going to be an acid. Any pH over 7 is going to be a base. So our first one here is 3.2 pH. We know it's an acid. And is it a strong acid or a weak acid? And I said, well, it's not a super strong acid because it's kind of toward halfway between the 0 and the 7. On the next one, the pH is 12.0, and that's a base. And because it's closer to 14, we say, well, that's a pretty strong base, right? They call it basic. It's strongly basic. Number 3 is 9.1. And if our neutral is 7, it's just a little ways up that scale. So we can say it's a low or it's weakly basic. It's not a very strong base at all. And then HBr, which we know is a very strong acid, it's got a pH of 0.5, so it is almost 0 in the pH scale. So it would be very highly acidic or strongly acidic. Okay, and that's it. We'll start with a study guide in a little bit.